for our future decision. So if you can start recording. Okay, I think it worked. Okay. So then I give the floor to Mikko for his talk, State of the Net. So if you can start the presentation. So,
all right.
And we are looking forward for the keynote.
Thank you. Thank you very much. And thanks to all of you for joining today. In 1992, I had a holiday. I went to Austria, the Austrian Alps. A couple of friends with me. We flew to Munich. We rented a car. We drove to Austria. We went to the Alps, to a small lake where we had a boat rented, and we spent a couple of days on a boat in the Alps in the summer, which was nice. 2 years ago or 3 years ago, I was chatting at our office with a guy who works in our IT department. I was having a new laptop issued, and he wanted to chat with me because he knew I had a very long history with the company. And we were speaking about how life was different when the company was smaller and all that. And somehow we ended up speaking about Alps and Austria, and I mentioned this trip. And this IT guy was young. He was like 25. And he asked me that, tell me, Mikko, in 1992, how did you organize a trip like that? Like, how did you find about this place you were going on? How did you rent a car? How did you drive from Munich to Alps? How did you rent a boat remotely from Finland? Because there's no internet. Well, there's no web. Internet existed, but web certainly didn't. And this was a great question because I had no answer. I honestly couldn't recall. I couldn't remember how the hell did you do things like these before the web? Like, how did you find where to rent boats in Austria when I'm in Helsinki and there's no internet, there's no Google, there's no nothing? I couldn't answer him. I had to think back. Eventually I did remember, of course. I mean, the way you used to do things like these before the web is that you would call directory service. Here in Finland, there would be a special phone number where there would be a person with phone books for all different countries. And you would ask him that, hey, I'm trying to find a boat renting place from this part of Austria. Do you have the yellow pages for the physical phone book for Austria? And yes, I do. Could you please search for some numbers? And I would write them down. Then I would call up the phone renting place and use my school German to try to figure out how to rent a boat. Same thing for renting a car. And of course, then when we're driving, there's no GPS, there's no electric maps, so you have paper maps. And I think it's a great illustration on how much the world has changed so quickly. And this, well, to me, it really isn't that long ago. And of course, it is a long time ago. But the world is changing now faster than ever before. Technology is changing the world faster than ever before. The internet is changing the world faster than ever before. And we are all living in the middle of a massive technological revolution. And it's kind of hard to see these revolutions when you are living in the middle of them. But it's easier to see how much the world is changing right now if you took the viewpoint from, let's say, 200 years into the future or 500 years into the future. Imagine someone writing a history book about our time, about the early 2000s. What's the most important thing? What's the most defining thing which has happened during our generations? What's the number one thing they would write about us in history book written in the year 2500? Well, the first thing they would say about us is that we were the first people who got online. Mankind lived on this planet for 100,000 years without the internet. We happened to be around when it became a thing, and internet will be part of mankind's future forever. We just happen to be living in the middle of this transitional time. And it's changing everything. Of course, it's changing everything, but it's kind of hard to see all of these changes happening because we are in the middle of it. Sure, the web came around 1992, 1993. I set up the first website for our company in April 1994, and I remember this well because it was website number 17 in Finland. There were 16 websites and we were website number 17. Today you couldn't count, of course, how many sites there are because there's too many. But the internet itself has been around for far longer, based on ARPANET, based on TCP/IP protocols. I was born in 1969, in October 1969. Basically, I was born 2 months before ARPANET for the first time connected two machines to each other, which you would think as the beginning of the internet. So this is how old the internet is. I'm 2 months older than the internet, if that's the way you think about it. And I honestly do believe that internet is the best thing which has happened during our lifetime. And I honestly do believe it's the worst thing which has happened during our lifetime. It has brought us so much good, so much improvement, so much new business, so much new connectivity, so many new forms of entertainment. I love the internet. But at the same time, it has brought us all these downsides, all the new types of risks, crime, the fact that conspiracy theories thrive now better than ever before. Clearly, it has its own downsides as well. And they're always exactly the same things when you look at it from the other point of view. Now, this revolution that we're living in has changed our lives, but it has changed the lives of minorities even more than majorities. And here, when I say minorities, I don't mean any specific type of minority, any kind of minority. Let's say you have a rare hobby. Before the internet, if you had a rare hobby, there was nobody in your town who would have the same hobby. You were alone, you had no support. And then the internet comes around and suddenly you find people like you with the same hobby as you from all over the world. You're not alone, there's tons of people like you. And we humans are animals, we're herd animals. We need the support from people like us. And that's one of the big upsides of the internet. Even if you belong to a very small group, even if you're different, even if you're a minority, you'll find people like yourself. And this same specific thing has a huge downside. You see, when people belong to, hold on, I have a signal call coming in. Soitas sua takaisin. The problem with Signal is that it's ringing on my desktop to my ear, so I have to do something about that. Sorry about it. And the thing about destructive minorities is that they get the same kind of support as any other kind of minority. Minorities like people who are suicidal or who dream about arranging school shootings or other types of terrorist attacks. They will find people like themselves. They will get the support from other people. It's exactly the same thing. It's great and it's awful at the same time. And we often say that internet is just a tool. Technology is just a tool. You know, they can be used for good or they can be used for bad. They're neutral. Sure, I agree. And then again, I don't. For example, when we discuss encryption technologies, well, encryption is a great example of an innovation which has brought us great benefits. Or security, for example, online commerce relies on encryption. Our online privacy relies on encryption. Great benefit indeed. And it brings us great problems. The fact that criminals can now also communicate safely and securely. Extremists, terrorists, bad people get the same benefits as we do. And once we invent something, we cannot uninvent it. We cannot make it go away. which means we can't restrict these technologies after they have been invented. If we invent something like uncrackable encryption, and then we think the downsides are too big, we can't really make it illegal, because if we make it illegal, then the benefits go out. We, law-abiding citizens, won't then use those technologies because it's illegal. But of course, the people who break the laws, the criminals, of course, well, they break the laws. So they will break that law as well. We can't uninvent technology. But it gets more muddy when you think about technologies like, let's say, cryptocurrencies, or let's say Tor hidden service. Sure, absolutely you can use cryptocurrencies for good, and absolutely you can use them for bad. Are they used more for bad than good? Well, we could argue about that, but many would say that there's more crime being conducted with cryptocurrencies than legal things. Or let's take an even better example, Tor hidden service. Now, I'm very well aware of the history of Tor hidden service, why it was developed, and how important it is for people living in totalitarian states. Sure, and I have no doubt in my mind that Tor hidden service is used more for bad than good. Yes, it is a tool. Yes, it can be used for good or bad. Yes, it's neutral as a technology, but still, I have no doubt that there's more badness being done with websites hosted in Tor hidden service than good things. All the illegal trade, all the destructive discussions. We can argue all we want about how technology is just a tool and how it's neutral, but it's not really true. And of course, our privacy has changed probably more than anything else because of this revolution that we're living in. Before the internet, we were relying on mass media to get the information we wanted. We would be reading the newspapers, watching the television, listening to radio. So it was one too many distribution of information. And then when social networks and technologies like YouTube became available, it felt like utopia. Like, wow, for the first time in mankind's history, now everybody can publish their thoughts to the world. Anybody can make a video, anyone else can see it. Everybody can start publishing. Felt like utopia, and now we've woken up that it's no utopia, it's more like a nightmare. This is the reason why conspiracy theories thrive. And these new technologies enabled closer tracking of citizens than anything we've ever seen before. Enabled information operations which can be used to sway the outcomes of democratic elections. And when we were getting our news from newspapers, the publisher of those news had no idea what exactly we were reading and what exactly we were interested in. You see, when newspaper was on paper, the only bit of data the publisher had was that I was subscribing to the paper. Today, when I'm reading my news from the website of that same newspaper, they know exactly how many seconds I spend on each article. They know exactly which topics I bypass and which topics I spend a lot of time on. They know exactly which politicians, when they are mentioned in the headlines, will make me read the news and which parties I will ignore. In fact, if you're wearing a smart watch, they will be able to detect which articles will increase my blood pressure and where I will stay neutral. Never before in mankind's history have we been able to be tracked as closely as we are today. We even sleep next to our tracking devices. We just don't call them tracking devices. We call them smartphones. But that's what we do. Internet is the best and the worst innovation of our time. And it's not just privacy that's suffering. Technology also shapes the way we fight our wars. It shapes the way we resolve our conflicts. Cyber weapons are a very real thing. Cyber war is a very real thing. And cyber weapons make sense. It makes perfect sense why militaries and intelligence agencies are interested in offensive use of the internet. Cyber weapons are effective. They are affordable and they are deniable. When you have a weapon which is effective, affordable, and deniable, you have a pretty good weapon. Especially the deniability part is important, especially for offensive use by entities like intelligence agencies. Spying has always been about collecting information, and information has changed. Information used to be physical, it used to be on paper. So if you wanted to steal this information, you had to physically come to the information so you could steal it. Today, most information is not like this. Most information is data. It's on our computers, it's in our networks. You don't have to go physically anywhere to reach that information. Exactly as crime has changed, because criminals don't need to travel anymore. Crime used to be local. War used to be local. The internet takes away geography, it takes away distance, it takes away borders. We used to have to worry about criminals who were living in our city. Now, when you get hit by crime, most likely the criminal is on a different continent because the crime happens online. In 1993, my home city of Helsinki, no, actually, my home country of Finland, all of Finland had 110 bank robberies. We had 110 bank robberies in our country in 1992 or 1993. The last time we had a bank robbery was 11 years ago. They've stopped happening. Instead, bank robbers have stopped going into physical banks with guns to steal physical cash, and they've started using online bank robberies, targeting credit card numbers and cryptocurrency exchanges to make their money. Completely global crime where geography doesn't matter anymore. And when we look at warfare today, borders still matter in the real world, but they don't matter in the online world. And modern conflicts like what's happening in Ukraine right now are fought in all the domains we have for warfare. That's land war, sea war, air war, space war, and cyberspace war. Now in Ukraine, we really shouldn't overemphasize the importance of cyber warfare, because most of the action in Ukraine has definitely been in the real world, not in the online world. But still, online warfare has definitely been part of the full picture of that conflict. And it's quite remarkable to see government officials openly recruit foreign civilians to participate in the war and point them targets, ask them to attack them online. So almost like science fiction, except it's not science fiction, it's happening right now. Also, I really had to do a double take when I saw that the Ukrainian cyber police, which is of course in a crucial position to fight Russian aggression right now, they've been collecting donations for their operations online, and they accept Monero donations. They are also selling NFTs to collect money for the Ukrainian government. So the police selling NFTs is weird, but even weirder is police accepting Monero donations. Because in my line of business, we only see Monero, the cryptocurrency, being used by online drug traders. That's basically the only use I've seen for it ever, except now Ukrainian cyber police is using it to collect donations to fight Russians. Five years ago, I invented a new term cybercrime unicorns. And here unicorns is a reference to unicorn companies, technology startups, which are valued to be over $1 billion in valuation. And the idea I had 5 years ago was that one day we might see cybercrime gangs, which are so successful in their attacks that we should be considering them to be unicorns. Well, unfortunately, I was right. Cybercrime unicorns are real. Cybercrime unicorns are here today. And they're not only here because cybercrime is making more money. It is making more money, but the real reason is that these kind of attackers have enjoyed the benefits of massively increased valuations of cryptocurrencies. 5 years ago, when I invented the term, we knew of several cybercrime gangs which were holding wealth of, let's say, $10 million or 10 million euros. Now, if you had 10 million euros in Bitcoin 5 years ago, and you just kept them there, you have €1 billion today, because the value of Bitcoin has increased 100-fold in 5 years. This is the real reason why we now see massively wealthy cybercrime gangs, which means they can invest into their attacks. And this is worrying, because now we see cybercrime gangs operating professionally, just like any traditional real-world cybercrime gangs do, by recruiting specialists, by recruiting lawyers, financial people, business analysts, by running their own data centers, by running their own support units, by building branding. Now, why would cybercrime gangs build branding? Well, think about gangs like, the biggest ransomware gangs. They all have websites, they all have brands, they all have names, because they need their victims to be scared. They need their victims to know of their reputation. And this is especially worrying because now over the last 2 years, we've seen a couple of instances where cybercrime gangs have set up fake security companies, including a company called Combine Security, which we saw, which was a penetration testing company recruiting pen testers for fully remote works, where your job is to do pen tests at client networks, find vulnerabilities that can be used to break in, and then write a report about them. And the people they hired were security people like you and me, who had no idea that this company doesn't exist. And the pen tests they are doing are being done into networks of companies which have not ordered a pen test. And the report they write will then be used by the criminals to break into these networks. The salaries they were paying were really nice, basically twice the salaries of legitimate companies. And the next step in that development will be that they will start hiring AI people and ML people. What will the first machine learning fueled attacks look like? I think they will start by simply automating their campaigns. When you look at modern malware attacks, like ransomware attacks, they need the actual operation, they need a target list, they need a distribution mechanism, and then they need the actual operational facilities. And these are all being run by humans. So let's say they use email to spam out malicious links, which link to a website with an exploit, which will then drop a ransomware on the computers. This means somebody has to write the ransomware. Somebody has to write the emails, the actual text. Somebody has to come up with the email lists of, let's say, 500,000 email addresses, and then someone has to operate all of this. Let's start sending out the emails. Are our emails getting blocked and filtered? Yes, they are. Let's modify the email and let's retry. Now we're getting through. Are the actual emails getting clicked by users, and do the actual URLs work, or are they getting blocked by content filtering systems? They're getting blocked. Let's change the URLs. Let's set up new websites. Excellent. Now our websites work. The actual binary is getting dropped onto their hard drive. Is it getting blocked by endpoint security or XDRs or EDRs or MDRs or antivirus? Yes, it is. Let's recompile the binary to make it go through. Now, all of this could be replaced with a fairly simple Python script. And when you add on a little bit of learning functionality, all of this could be automated permanently. And this hasn't happened yet, but it will. And the fact that we have cybercrime unicorns amongst us will make this reality faster than we would like it to become a reality. Our work, the work of security people, matters today more than ever. Everything is becoming digital. Every company is a software company. We all want to be able to use our system safely, securely, and in privacy. We have to try to do all of these things at the same time. And our enemy is becoming more wealthy and more powerful. And then we don't only have to worry about criminals, we also have to worry about foreign government, foreign intelligence agencies, and foreign militaries. This means that there is, how should I say it, job security in security. There's job security in security. The internet is the best thing and the worst thing which has happened during our lifetime. And even though my trip to Austria in 1992 happened just a moment ago, it really happened a lifetime ago, in a different world, in a different time, in a world without the internet. The world is changing so fast we don't even notice it. Thanks for joining us. Thank you for your work. Thank you very much.
Thank you, Mikko, for the fantastic talk. And I think indeed it is worrisome to look at the current state of the internet. And yeah, so I suppose yeah, we need to be proactive in the whole cybersecurity community in Europe and all over the world. So first, I would like to take some questions if you have any to our keynote speaker, Mikko. And please raise your hand. And if you have any, like, we can have a short discussion. Yeah, you have any questions? So maybe from one question from my side, Mikko. So you talked about this AI-enabled attacks from the cyber like the gang, you said, right? Like the
cybercrime unicorns.
Yeah, cybercrime unicorns. So how do you see ourselves this resilience from the European cybersecurity community? Like, do you think that we should also go against like active type of defense, like in line of? So, and how do you see the scope in next 10 years? Like how it has potential, and how it could develop?
The only thing which can stop bad AI will be good AI. The good news there is that good AI is reality. It's in everyday use, unlike bad AI. Whenever I discussed with journalists about criminals using machine learning and AI, and I tell them that, you know, we're not really seeing it yet, but we will see it soon. Very often I get pushback, and no, of course they're using it already, and I've read about attacks using machine learning. And then when I ask for details, it either goes down the route that there was this phishing attack which was using deep fake voice technologies to sound like a boss, which may or may not have happened. We've never really seen evidence of that happening. Maybe it's just a guy who sounds like the boss, who knows? Or it goes down the route that there's this paper about attacks, which is an academic paper or an industry paper, which is theoretical. That's not real. That's a theoretical attack. But like I said, security use of ML has been around forever. In fact, it's quite surprising. The first machine learning program we started at our company was in 2005. 2005, 17 years ago. 17 years it's an eternity ago in this space. But that's when we started automating our malware replication and detection systems, basically automating the work of our analysts in the lab at the time. So how do we know bad guys are not already automating these campaigns that I described? Because our end of this picture is already automated. Whenever they send out emails or modify the URLs or recompile the binary, our reaction is very quick. Security companies react automatically with automation. So it came of ping pong, where the pong from our side comes always immediately. And then they need a lot of time to adjust because it's done manually. When both sides use automation, then the game will be ping pong, ping pong, ping pong, very quick. Everybody, both sides will react automatically, and the rate of attacks will escalate. We will not be missing when this happens, and it simply hasn't happened yet, but it will happen soon.
Okay, so thank you for the answer. Yeah, it will be tricky, I suppose, like when the AI comes into play, and how this will the scenario will look like. Yeah. Okay, so yeah, so I do not see any questions. So if you have any question, like you can always be in touch. I think he's very active in Twitter. I think like we can also if you have one question, we could tag you, I guess.
Sure.
And yeah. So and I so from our side, we appreciate very much that you joined us and gave your thoughts and for the keynote. So we so next talk will be from Martin. Yeah. So please, the floor is yours.
Can you please confirm that you can see the full screen?
Yes, it is. I could see, but I could see also your comments. So maybe you need to do the full screen.
Okay. Start sharing differently. Is it better?
Yes, perfect. Yeah.
Thanks.
Okay.
Okay. So thank you for a great introduction, and I hope that some of the points that I will make in my presentation can, let's say, at least tackle some of the issues that were raised during the keynote. So my presentation will be about sharing new type of threat intelligence, and I will give some use cases to explain where we envision that such an intelligence can be used, and then also briefly introduce the threat intelligence itself. And in the end, I'll mention some standardization effort regarding our threat intelligence, in particular cybersecurity playbooks. So what was our motivation? We set up several, let's say, research topics that we want to address within the SAPPAN project. Namely, it's to improve the detection capabilities, to improve privacy when sharing threat information, and to improve also reaction on some attacks and incidents. And basically researching these various topics we had various ideas how to address them, and some of the concepts we came across, we used to and applied them in a new way in a threat intelligence sharing domain. So within this threat intelligence sharing domain, our goal was to extend the threat intelligence with new type of information while preserving the privacy if possible, and at the same time to enable sharing, to support the sharing of such a threat intelligence. And by defining these goals, we wanted to address the increasing, let's say, set of tools that are being used by attackers, the evolution of malware, also the rising complexity of detection and how the attackers try to avoid the detection, as well as the automation of attacks. So let's go straight. So what type of new intelligence are we talking about? We let's say introduced or focused on two data, let's say, types. And the first is the machine learning classification models, and the second is playbooks. So let's first focus on the machine learning classification models. We consider that the machine learning classification models, the classifiers, they can be the new indicators of compromise. And why we think that? Because they can capture more information. They have better expressive power than, for example, an IOC that we are using today. For example, if we use a file hash, we have a hash of a particle file. But when we use a classifier, then we can probably classify the whole family of the similar files. And we can continue to other type of problem, not only files, but we can classify behavior. We can classify what we have seen. We can classify a list of domain names. So we think that the machine learning classification models will become or can become at least a new indicators of compromise. How it can work? We studied two types of use cases. One is the, let's say, the indicator of compromise, and that is there's one organization that has the machine learning capability, which means that the organization has data, usually annotated data, which enables the organization to train a classifier. And then the classifier is shared with other organizations that do not have the data. They receive the classifier and they can use it to analyze, for example, the data from their infrastructure. This is a, let's say, IOC example. To be, let's say, specific, let's consider distributed denial of service attacks, and let's consider some organization that is under such an attack, and such an organization can describe the attack by a DDoS fingerprint, and the DDoS fingerprint can exactly be a machine learning model. In particular, at SAPPAN, we investigated how to use decision tree to represent such an attack. And actually, the decision tree can be represented as a set of and/or rules. So that's simple. But if we consider some more advanced machine learning models, such as random forests or neural networks, then we cannot no longer represent it as the rules, and we have just the model. And we can use it actually to inform other organizations that there is such an attack. And if then we took the second component that we are also presenting in this presentation, the playbook component, then we can connect. If you see such an attack, then you can use such a playbook. That's the first use case of using the machine learning model and sharing them. The second use case that we've been investigating at SAPPAN is how to improve the detection capabilities. And in here, we have specific example where multiple organizations are able to train their classifier. So they have the data, they have the capability, but they all want to have a better classifier. So they would ideally like to collaborate in the training the classifier, but they fear sharing of the data, of the raw data. Therefore, we investigated various approaches, and in this particular example, we use federated learning approach, where only the improvements to the model in a single epoch of training is shared with the others. And by sharing the local improvements of an organization with other organizations, the organization arrive at better classifiers, at training better classifiers. So this is the second example of using machine learning and sharing the machine learning classifiers. Of course, maybe in future we can come up with more, but this is what we investigated at SAPPAN. What we did is we integrated sharing of the classifiers in a MISP. So we selected a MISP threat sharing platform as our primary, let's say, prototyping platform, because it's quite popular, used, and supported. And we prepared a MISP object to represent the classifier. And the classifier, the MISP object is not specific to a particular machine learning method. It can carry classifier, be it either random forest, be it a neural network, doesn't matter. So it can serve also multiple use cases. It can serve both the use cases. It can be IOC, or in a different case, it can serve organizations to participate in collaborative machine learning. And actually, it's quite simple. It's just an object where there are metadata which describe the model format. So, for example, if it's HD5 or other type of representation, then the use case, so what type of problem is being used, the description, of course, you need to describe when you are, for example, using the classifier, you need to know what are the inputs and what are the outputs. Then the unique ID might be useful during the collaborative learning to represent the epochs, and then the classification model itself. This was a little bit simplified, but it's like that. And yeah, we prepared the prototype and tested it. And we were successful in training a better classifier, which I believe then a colleague of mine will talk a little bit later on in the next presentation. Therefore, I will focus on the second bit of the presentation, and that are the playbooks. So why do we need playbooks. Basically, the motivation is to describe the playbooks, basically describe the response and recovery steps, but maybe they can also be used to not only response and recovery, but also to during the preparation cycle. So they can describe even the steps how to prepare for an attack to come. When we want to share the playbooks, we want also the other party to understand the playbook. And ideally, we do not want only a human to be able to read the playbook, but we want a machine to read the playbook and ideally also to understand the playbook and then interpret it. The playbooks are also sometimes called workflows if the playbooks are not high level but are already at the machine level. They are either semi or fully automated, which means that some require a human to intervene during executing the playbook. Some do not require it at all. And about the playbooks, it's nice that the playbooks brings a repeatability in the process. It's basically a guideline of steps what to execute, which is very nice to document the process, to monitor the process, and to improve it. And by sharing, we can sharing such information, we can improve it either collaboratively or in another model. There might be playbooks shared based on some commercial agreements. So similar like in sharing ideas rules, there might be an open version as well as a commercial version. So at SAPPAN, we worked on how to capture the response and recovery steps into some workflows. And we come up with a SAPPAN format, but in parallel also there was an OASIS activity which introduced Cacao standard. So in the end, we decided to go with Cacao and let's say consider this as let's say future for the playbook sharing. And therefore we took the Cacao specification and decided to integrate again the Cacao representation of playbook into MISP. But again, we didn't want to prevent also other formats of playbook to be shared. Therefore, the specification is general, and the MISP object can host also other formats. And the MISP object consists of metadata, again describing the playbook itself, such as the playbook standard. So if it's Cacao or if it's SAPPAN or if it's other type of playbook, for example, described as BPMN, playbook type. So if it's described in JSON, XML, description, what it's about, what person roles are involved in the playbook, if any, what's the level of abstraction, if it's a high level at the level of guidelines, or if it's already executable workflow, how long, if there's let's say limited validity of the playbook, so if the lifetime of the playbook should be somehow restricted, and then the playbook itself. So this let's say general description then allows to accommodate any playbook and does not require to introduce new object with a new playbook standard. And how it may work in, let's say, the context of an organization. So we envision that an organization has a database of playbooks, and this database of playbooks is some of the playbooks are shared if they are useful. For example, if we report some incident as a search team, I'm, let's say, a little bit affiliated with a third team of CESNET, and CESNET connects multiple organizations and reports them incidents. We want the organization to know what they should do when they see an incident, when they receive the report. So that's how we can express what are the next steps, what they should do. So we report the incident, and ideally we would like to attach the playbook so they can act upon based on the playbook. And ideally at SAPPAN we also went a little bit further, and we tried to, if it's a high-level playbook, we tried to translate the playbook into a workflow that is more machine executable, and then this workflow can be executed by a response automation, which later on in the during our event will be presented also by my colleagues. So let's say just a few slides about the standardization to explain what we did. So at SAPPAN there was a whole task to capture the response and recovery steps and to standardize them. We introduced the standard in the deliverable at the same time where the first standard of the Cacao was also introduced, and that's how we got aware of the standard. So we decided, okay, what can we do? At least we can, let's say, take this further. So we got in touch with the technical Cacao committee, became a member of WESIS, discussed our next goals. Those were to make it shareable via MISP in particular, and therefore we made the implementation and created the MISP object. The MISP object is now in the official MISP repository, so you can use it. And yeah, we described our joint effort in a paper. And that is to conclude my presentation. So basically what to take away. We think that we need, let's say, more complex type of IOCs to face the new threats. This new IOC could be, for example, the machine learning classifiers. There is the second use case of collaborative machine learning, so to improve collaboratively our capabilities. And then the second bit is in the playbooks, where we hope that the playbooks can serve for automation of reactions of the steps, how we react to incidents. We prepared also the first prototype in case of the new IOCs. We are in touch with another European project called Concordia, and they develop a DDoS clearinghouse, and exactly they like the machine learning model to represent the fingerprint of a denial of service attack, because so far they fingerprint the denial of service attack only based on the IP addresses. So this gives far better representation of the attack. So that's where we plan to go further with machine learning, with the classifiers as IOCs. And regarding the Cacao, we stay at the Oasis, and we will, let's say, test our representation of the playbooks with multiple companies in the future to see whether there's something missing and whether it's viable. And yes, in the future, I expect that either open source communities or various business models will be introduced, and hopefully some of the concepts will make it to be, let's say, practically deployed in the end. And that's the conclusion of my presentation. Thank you for attention.
Okay, thank you, Martin. Thank you for your interesting presentation. So I would like to ask our audience if anyone has any questions. You can also type your question in the chat, and Martin can try to answer it. Okay, so I don't see any specific questions. So in that case, I suggest like we move to the next presentation, and that will be from my colleague Arthur Drichel from RWTH University and Hugo Hromic from HPE Ireland. The talk will be about SAPPAN innovation in DGA detection.
Yes. Exactly. Can you see my screen?
Yes.
Perfect. Okay, I guess I start then.
Yes,
okay.
Please go ahead. Floor is yours.
Thank you. Yeah, my name is Arthur, and together with Hugo from HPE, we will present the SAPPAN innovations in DGA detection. So to get started, let's first introduce what a DGA is. So let's first have a look at traditional botnet communication. Usually a bot has two approaches here. It will either use a fixed IP address or a fixed domain name in order to get the IP address of the C2 server and thereby to communicate with the botnet herder. So from the perspective of the botnet herder, this has a major drawback, as the defender can easily block this connection establishment attempt once these values are known. So this is why modern botnets rely on domain generation algorithms and short DGA. And DGA is a pseudo-random algorithm that generates a huge amount of domain names, which are subsequently queried by the bot in order to obtain the command and control IP address. The botnet herder usually only registers a small subset of the generated domains. Thus, most of the queries result in non-existing domain responses, and only the one query results to a valid IP address for which the botnet herder registered the domain in advance. And he is capable of this because he knows the generation scheme. These NXDs can be analyzed within a network in order to detect DGA activity, but the non-existing domain responses are not only generated by bots, but also are caused by typing errors, misconfigured software or outdated software, as well as by the intentional misuse of the DNS, for example, by antivirus software. So in the past, several DGA binary classification classifiers have been proposed, which try to separate these malicious domains from the benign domains. And these classifiers also achieve high accuracies. And this is called the DGA binary classification task. I'm going one step further. It might be desirable to not only detect DGAs, but also to attribute them to the domains, to the DGA that generated them, in order to allow for targeted remediation measures. And this is, of course, more difficult as a binary classification task, as there are already over 92 DGAs known. So in SAPPAN, we had the use case of DGA detection, and we focused here on a research-driven approach. In total, we already published 7 papers in the context of DGA detection, so only on the context in DGA detection, and an 8th paper is already under review, submitted and under review. And however, we not only focus on the research, but we also keep in mind that we want to apply it in the real world. And therefore, during our research, we ensured that the classifiers are real-time capable and scalable. And we also put integration efforts and integrated our research already into existing security information and event management solutions. So here on the right side, you can see a word cloud, which contains a lot of aspects we have covered during our research. And in the following slides, I will try to represent selected results from our research in 1 or 2 slides each. So in SAPPAN, we started with the DGA binary classification task. That is to say, we wanted to separate DB9 from the malicious domains. To do this, we proposed a neural network classifier, which is based on residual neural networks. And here in this figure, you can see its structure. And these so-called ResNets, they introduce so-called skip connections. You can see it here, which ease the training and counteract the vanishing gradient problem. We compared our binary residual neural network-based classifier with the state of the art and could show that our classifier reduces the false positive rate and works very well. And during this study, we also focused on 2 different aspects. The first aspect is generalization. And here we train the classifier in one network and then evaluate the classifier on real-world data from a different network. And we could show that the classifier generalizes very well, and therefore the classification could actually be outsourced as a service. The second aspect we investigated was whether the classifier is time robust. So we trained the classifier on data from one point in time and then evaluated the classifier on data even which was captured 17 months later. And we could show that the classifier is time robust. And of course, the false positive rate slightly increases, but it was still manageable. And of course, if you want to have a classifier that works best, you would use still frequent retraining. And to ensure its real-time capability, we tested the classifier in a large real-world network and classified a whole 1 month recording and showed its feasibility. We then continued with the multi-class classification task, and here we wanted to attribute a domain either to the B9 class or to any DGA that is known in the training data. And here we also proposed a ResNet-based classifier, but this time it was deeper. It consists of 11 residual blocks. And here on the right side, you can see a confusion matrix, which is used to visualize the performance of the classifier. So at the top left corner, you can see the B9 class, which is separated very well from the other classes. And on the y-axis, you can see the true label of a sample. And on the x-axis, you can see the predicted label of a sample. So a perfect classifier would actually yield an identity matrix. And what you can see is that the classifier is working remarkably well, as most DGAs are detected with high confidence, but there are still some outliers. For instance, here, this is the DNS benchmark. And the reason for this outlier, for instance, is that they use data source. So we used the DG Archive open source intelligence feed, and it contains only 5 samples for this specific DGA. And since we used 5-fold cross-validation, we trained a classifier on 4 samples and tested on the left out sample from the training set. And if we classified this one sample wrong, then the whole score of the specific class degrades to 0. Again, we did a comparative study with the state of the art and could show that our classifier requires 30% less of training time. And we could also show that we achieve an improvement of over 5% in macro of 1 score, which corresponds to the fact that our classifier is able to detect several classes with high confidence, which the other state-of-the-art classifier cannot correctly detect. And again, we tested this classifier in a 1 month recording and could show that it is real-time capable. The 2 classifiers I have presented you are deep learning based, and therefore they heavily depend on the used training data. And as you could see on the example of DNS benchmark, the sample distribution is heavily imbalanced. This is why we investigated in SAPPAN whether it is beneficial to include underrepresented DGAs into the training set. And for this, we conducted a comprehensive study, and for both classification tasks, we showed that it is beneficial to include those samples. As for the binary classification task, we could improve its detection performance by over 10%. And in case of the multi-class classification task, we could show that for 22 of the 46 weakly represented classes, we could reach an F1 score of over 90%, and for 11 classes, even an F1 score of over 99%. The major important aspect here is that no significant influence on the classification of the well-represented classes could be measured. So it's definitely beneficial to include them. On the other hand, if we would omit these samples, then in a real world, the classifier would still have to deal with them because they can appear in a real world network. And therefore, to model this, we did an experiment in which we trained the classifier on samples of the well-represented group, and we classified samples on the weakly represented group. So this is the classifiers we left out, and this is the classifiers we trained on. And as you can see here, a huge fraction of samples is actually classified to the benign class if left out, and this is so this corresponds to the fact that an intrusion detection system would miss these samples entirely, and not that they are just classified to a different malicious class. So again, it is definitely useful to include weakly represented DGAs into the training set. Even though the proposed classifier achieve high accuracies, they are still deep learning classifiers, and thus they behave like black boxes. And therefore, it is difficult to evaluate their line of reasoning, as this results in a lack of confidence, because it is unclear why a sample is either classified to the benign class or why a classifier classified a sample to either one of the DGAs. So this is actually also the reason why security analysts prefer simpler solutions such as decision trees or even rule-based systems. And to counteract this issue, we developed two approaches in SAPPAN. The first approach is based on a visual analytics system, which tries to provide understandable interpretations for predictions of deep learning classifiers. And I don't want to go into detail here, but the main idea is that we cluster the activations of the model's neurons, and then we leverage decision trees in order to explain these clusters. The second approach is based on the idea of explainability by design. And for this purpose, we developed a feature-based classifier, explain, which is based on random forest, and we evaluated it, and it's competitive and contextless. And the main idea here is that by using feature-based approach, we can easier interpret the predictions as they can be traced back to a characteristic of the used features. Again, on the right side here, you can see the confusion matrix, but this time it's a combined confusion matrix. So the upper left part is dedicated to the feature-based approach, and the lower right part is dedicated to the deep learning-based approach. And what you can see here is that it seems that the deep learning-based approach learns similar features as we have studied for the feature-based approach, as the classifications are very similar. And in total, we studied 136 contextless features, 42 of which we gathered from related work, and 94 were newly developed. These features can be divided into three different groups. The first group are linguistic features, and they, for instance, count the numbers within a domain or compute the foveal ratio. The second group are structural features. This is, for instance, the domain length. And the last group are statistical features, and they, for instance, compute frequency distributions of certain engrams or the entropy. And again, we tested the classifier and ensured its real-time capability. As Martin have said in the previous talk, a big aspect in SAPPAN is the privacy-preserving intelligence sharing. And here we wanted to increase or improve the detection performance of a classifier by collaboration. But of course, we can't share raw data because it contains sensitive information. For instance, if we would share the domain names of one network, then of course it might be possible to reconstruct the browser history, for instance, of an employee within a network. And also, not only the raw data contains sensitive information, but also the models may leak sensitive information. For instance, they can be attacked by a membership inference attack, and then you could reveal or try to reveal training samples used in the model. And therefore, in SAPPAN, we improve generalization performance by sharing intelligence at different stages of the model training, and we do this in a privacy-preserving fashion. So the naive approach would again be the raw data sharing. Here we propose to use different anonymization techniques and also the application of Bloom filters, for instance. The second approach is after the model training. And here, for instance, ensemble classification can be used. So every party trains an own model, and then they do combine the models, for instance, by majority voting in order to come to a final result. And another approach here is feature extractor sharing. And here we only share parts of the model to which we refer to as a feature extractor. And the main idea here is to, by sharing less information, we have less information leakage of sensitive data. And of course, information sharing is also possible during the training of a model. And for instance, in federated learning, we share the updates of the weights. And in the teacher-student approach, we train a student classifier based on the predictions of teacher classifiers. And we conducted an empirical study, and there we could show that the feature extractor sharing and federated learning perform best. And there we could show that we can achieve a significant reduction in false positive rate by up to 50% compared to a single party approach. And here we also ensured that the reduction rate of the false positive rate correlates actually with the increasing number of parties that are collaborating. And thereby we could ensure that the collaboration actually works. And we also conducted a preliminary privacy utility trade-off study in which we could show that, for instance, for the federated learning approach, we can ensure the protection of the privacy with a manageable overhead. Another thing we investigated in SAPPAN is privacy preserving classification as a service. The reason for this is that for well-performing classifiers, real-world training data is mandatory, but this is always not available for everyone. So, and also a second aspect would be if you would, for instance, like to do DGA detection on resource-constrained devices such as smartphones. And here the main idea is that we have a client that is the data owner, and he or she wants to classify or get a prediction for a data item, a domain name in this case, and this is sent to the model owner. And of course, this cannot be sent in plain. As I said, the model owner could reconstruct, or he knows then what the client is visiting for websites. And also the calculations done on this side should not be leaked to the client, as the client could try to steal the model or could try to get information about the used training data here, and should only receive the prediction. And in related work, several privacy-preserving machine learning frameworks have been proposed in the past. And the naive application of these frameworks to existing DGA classifiers resulted in an additional cost of inference latency of 13 minutes, or even communication effort of 234 gigabytes, which is required for a single inference. So we conducted again a comprehensive study in which we analyzed different homomorphic encryption and secret sharing based approaches to secure multi-party computation, and we proposed several model simplifications. And these model simplifications result in a reduction in inference latency of up to 95% and a reduction in communication complexity of up to 97%, while obtaining an accuracy penalty of less than 0.17%. Of course, these numbers I mentioned here are worst case scenario numbers. If we apply these model simplification on the average case, we obtain inference latencies of several seconds or even under 1 second, but still this is not enough for real-time classification, thus still future work is required. Now I briefly mentioned current and future work, and in the future work we want to improve the robustness of the DGA classifiers against adversarial attacks. And in a preliminary study, we already showed that the NX classifiers are more robust against adversarial attacks compared to classifiers that are trained on resolving traffic. Here you already get the advantage of using NX data, as for instance, the activity of a DGA is detected earlier than it can actually partake in any malicious action, as it's still trying to resolve to a valid command and control server IP. And also the order of magnitude is less than the order of magnitude of full resolving traffic. And in future work, we want to generate different adversarial examples and use them in different training sets to perform adversarial training in order to improve then the robustness of the classifiers. Further, we already developed a new DGA detection system, which is in the paper, which is currently under review. And but in another real-world experiment, we already could show that we could detect 6 unknown DGAs and 1 unknown seed of a known DGA. And our goal here was to develop a new DGA detection system, which is adaptive and also, of course, real-time capable. And the final goal of our research would be combining all research together to a single detection system. So this was the quick summary of several selected results. But maybe a short, very, very short overview on the implications of our research. So we improved the state of the art in various aspects. As I said, we have published 7 papers on DGA detection. 1 is currently under review. And we published a binary and multi-class detection model. And also the explain classifier is open source available. It is well documented, so you could actually try it out. And it contains everything, the whole classification pipeline, including hyperparameter optimization, feature selection, and so on. And our classifiers are, as I said, real-world applicable. And we also integrated our research already in existing CM solutions. So here you can see a screenshot of one integration of one partner of us. And the goal of this integration was, of course, to improve the detection performance and also reduce the false positives and providing explanation for predictions. And another integration is now presented by Hugo from HPE. And yeah, Hugo, please.
Okay. Okay. Hello. Can you hear me, right?
Yes. Yes.
Okay. Okay. So yeah, in HPE we wanted to implement what Arthur has been describing, the DGA classifier from SAPPAN, and the idea was that we needed to design the solution to integrate seamlessly with our existing infrastructure and platform. To prove that it's real world applicability, right? So we have a flow processing pipeline platform where we receive a lot of observability data from different sources, including web proxies, firewalling devices, and a number of other sources. So we wanted to apply the SAPPAN DGA classifier to one particular kind of data, which is from web proxy, which has the required request URL property in the data that we could classify to determine if it is malicious or non-malicious domains. Okay, so in our stream we have what is in the screen, a number of streaming events that have with timestamp, the source IP address, the destination IP address, and the request URL that the client tried to attempt from inside the HPE network to outside. So you can see different examples. These are mock-up examples. And then the idea is that the classifier, that the DGA classifier is not truly stream-based. So what we have to do is to create tumbling windows of a fixed size, for example, 10 minutes, where we will be accumulating events from this stream to go to process into the DGA classifier at the regular intervals. So for example, in the screen, you can see that we can build 3 different input windows every 10 minutes that will have a number of different events inside. And then we send them independently to the DGA classifier that will then reply with the results of which events of them were classified as malicious or non-malicious. And finally, we will be storing these results into a store, a document store in this case, for further visualizing by our analyst team using a tool called Grafana. Now, this DGA classifier, initially we implemented it with a very simple model that was given by the team from Arthur with a mixed result, but then they provide us with federated model, which greatly improved the false positive result that we were getting initially. So definitely the federated model proved to be better than with our real data. than the basic models. And another thing that I wanted to highlight is that Grafana is actually an observability visualization tool, typically used for metrics and of running system. But we wanted to use it because our analysts are very used to this tool already in the company, and we wanted to reuse that know-how as a simple extra dashboard instead of having to deploy a completely new tool for them. So we are showcasing here how to integrate this completely into our workflow using the DGA classifier under the hood. This was also designed to be pluggable and modular into our platform, so we don't have to modify or stop the production flow passing by on the system. So we also managed to very easily integrate it like that. In our platform. It runs in parallel to our streams, providing data to Grafana. So I want to quickly share my screen now because I want to show. Okay, let's say that. Okay, now I probably will be able to. I want to show you the dashboard that we created for this application. Let me know when you can see my screen.
Yes, we can see it.
Okay, so this is Grafana. We have this dashboard. We created this dashboard from scratch for the application of the DGA, and we created a number of panels that are in real time getting data from the document store that we chose for storing the result of the classifier. So first on the left, we have this malicious domains dashboard, panel that shows all the detected malicious domain from the DGA at different windows. And the number of sources, IP addresses that referenced this domain at the time, right? And on the right, we have the opposite, which is non-malicious domain, which usually are much many than the malicious ones, right? And then in the bottom panel, we can see details of both the malicious domain found and the non-malicious domain found in real time. So, for instance, I'm right now showing you results from the last 12 hours. This is constantly running for several weeks now. So in this case, the DGA was able to find these 3 malicious domains. This is the confidence that the model provides as well. By the way, I forgot to mention that we are using the binary classifier model here, not the multi-class. We also tested that one, but we wanted to keep it simple for the first proof of concept, like you are seeing here. So this is the confidence that comes straight directly from the model at different times. So these are 3 domains, for example, that were found in the last 12 hours. And in here in the details, for example, if I open this one, newspring.kr, we can see from which IP address this domain was tried to access in our web proxy logs, the company-wide. Okay, so if I do this for the APAN, it's the same. I can see here. For the case of non-malicious, I also have the same sort of information. So, for example, if I click just randomly one, I also can inspect it. So the idea here is that the analyst officer employee that is monitoring constantly the company can have this dashboard in running in real time, and then when the domains that are clearly malicious, either by confidence level here or by visual inspection, can quickly go here and or retrieve the IP address that was trying to access that, and then use other systems that we have in place to track down the owner of this IP address, the location, and then further investigate quickly what could be generating this malicious traffic, right? So for instance, I can here go even more, like 2 days, for example. And I would be getting more data from historic data. You see, so here we have even more domains like these ones that look very suspicious, right? And again, I can inspect here from where they come. So this is very convenient for us. We definitely are looking forward to a more adaptive result because there are a lot of, as you can see, the other sort of domain that we see, there are a lot of mistype domains that sometimes get classified as malicious. Sometimes, actually, this is what improved much more when using the federated model. With the basic model, a lot of typos were classified as malicious with very high confidence, but this reduces a lot after the federated model. So yeah, this is an interactive tool in that regard, because it's constantly getting data from the service that is running, and we can scale it as much as we need. We found that it's actually quite capable, as Arthur mentioned. It's able to process several thousand domains per request in a very short time. So the window that we chose here is 15 minutes. So we create 4 classifications per hour, basically, to don't crow or pollute too much this visualization. But this feed that the web proxy feed is having around 2,000 average events per second in the source stream. So we could apply this to bigger volumes of feed, for example, not only for the web proxy, but also we could implement it in the firewall observability data, where we could resolve with domains are not being resolved, sorry, and pass it through the classifier as well and display it like this. So yeah, I can say that this classifier was very easy to integrate in our platform. This was it proved to give a good interesting result to go in specs, and more importantly, it greatly reduced the time that the analyst has to be looking into this data, because it's just a very small sample of data that they have to go inspect. So for example, for the last 30 minutes, there was no suspicious domain in this case. So it's very tidy in that regard. So yeah, I think that is what I have to show here. If any question, I'm gonna give control back to Arthur now.
Well, yes, this concludes the talk, I would say.
Thanks, Arthur and Hugo. So there is some questions from the audience. So if you can try to answer it. So in the chat.
Yes, so the question from Pavel: when I try to give these 3 malicious domains to VirusTotal, they are all claimed to be safe. What do I miss here? Yeah, maybe they are false positives. So even though the accuracy is like 99.99x%, of course, the false positive rate is at 0.0001.
Maybe I have another explanation.
Yes, they are maybe not trained on the so we don't had the HP data, so they're not trained on HP.
No, I mean, in VirusTotal, usually people submit domain names that they know that are used for hosting, for example, some malicious content or things like that. But please be aware that these are not non-existing domain names. These domain names that are generated by algorithm, they are not registered yet. Attacker register only some of them to actually let the botnet to connect to command and control servers. So this is a non-existing domain name, and therefore probably the virus does not know it.
Exactly.
Okay. So thank you, Martin, for the answer.
I wanted to also complement that answer, that in the regard of training data, it's true that it's a big challenge to get training data, because first of all, we don't have it. We don't have data to say this is malicious, this is not malicious with our data. And I expect many other companies to not have this sort of data. Where we see the value of the federation is that we can make a model that works for most of us without having to have big data ourselves. And we were thinking internally as well at some point that this dashboard I showed you could incorporate some sort of feedback loop from the analyst, like when the analyst, which is the actual human that goes to check those results and verify if they are of concern or not, they could be providing like with a button or something. Okay, I went to check this and I found that it was not malicious, or I effectively found that it was a domain that was used for a C2 machine, and so on. So there is definitely room for improvement to provide or to build training data that we could later use for retraining the model, right? But yeah, it is. I want to acknowledge that it is a big challenge to not have training data in our organization.
Okay, thank you, Hugo. So I think we're a little bit behind time. So the next thing is to have a quick break. So I suggest we come back around in 5 minutes. So let's have a quick a toilet break, and then we go to the next talk, response recommendation and automation. Okay. So yeah, so see you in 5 minutes. Okay, I think we can start. So the next talk is response recommendation and automation results from SAPPAN. So this talk will be presented by three presenters, David, Martin, and Mischa. So floor is yours, David.
Great, thank you. Can you see my my screen okay?
Yes, yes.
And hear me okay? Okay, great.
Yep.
Yeah, so thanks. So yeah, I'm David Karpuk from F-Secure. I'll be giving the first 1/3 of this presentation on the incident similarity and clustering technology that we've been developing at F-Secure. So the motivation behind incident similarity is simple. So given a security incident, an analyst would like to get a list of all incidents that are very similar in some sense, to be made slightly more precise in a minute. Why would they want this? So say a security incident comes in and it's not clear immediately how to deal with it. It's not clear if it's a false positive or it should be classified as a confirmed incident. These things kind of depend on the organization, et cetera, et cetera. So a useful bit of contextual information would be how were past incidents treated. If they were very similar, say like, oh, in this organization, such and such type incident is often classified as false positive. There were 5 of these in the past month. They were all classified as false positive by some other analysts. So let me go ahead and say this one's a false positive too. This is sort of the idea. So essentially what we want is a way to measure similarity between incidents. So to get a little bit more precise, I want, given 2 incidents, I want a number, their similarity that's between 0 and 1, 0 being not similar at all, 1 being completely similar. So how am I going to design this function? So we vectorize the incidents, and the similarity is just the cosine similarity between the vectors. So if I have 3 incidents here in my little picture, a red one, a green one, and a blue one, you see the red and the green one are very similar to each other in terms of the angle between the vectors. So I might say that, okay, I have this red incident, I'm not very sure about it, but let me query this incident similarity model and see what the similar ones are. Ah, this green one's very similar. And that was actually a confirmed incident, so maybe I have to dig a little bit further into this red one to see what's going on. The blue incident, because the vectors are not similar in terms of the angle between them, we'll get a lower similarity score to the red one. So I'm of course sweeping all the magic under the rug here. Vectorized incidents is that's the whole game. And I won't go into this, but the magic and the art is all in how you take a security incident and turn it into a real valued vector. So this is our incident similarity technology. It's in production now, being used by our analysts and our customers. And built on top of that is our incident clustering technology. So what do I mean by incident clustering? I just mean that we want to group the incidents together, all of our incidents together, in such a way that within a group, within a cluster, all the incidents within that cluster are highly similar to one another. And what would this do? Well, you could process incidents in batches, right? I click a button and I select all the incidents in cluster 100. If I know that 3 of them are false positives and all the others are highly similar, then I could go ahead and mark all of those false positives in MOS. So this kind of batch processing of incidents is very helpful. And if I could sort of even more exciting is the idea of kind of monitoring the threat landscape over time, right? So if I can track the incident clusters over time, if I can measure kind of how they change, how they merge, how they split, I can say something about the general trends in the threat landscape. And this gives sort of some very like a higher up contextual knowledge to our analysts. And then maybe on a specific basis, I might want to take an incident, find out what cluster it's in, and use all the contextual information provided by that cluster to make a decision about how to process that specific incident. Okay, so how are we computing this? We're using a method called agglomerative clustering. It's also known as hierarchical clustering. And this particular clustering technique is used to guarantee the property that everything within a cluster is similar to each other. So it's currently the current method of clustering. It's retrained weekly. So every week we take all the incidents in our database and we assign them to a new cluster, and we forget everything about the week previously. But in production soon, we'll have a more online streaming clustering algorithm, which takes incidents in as they happen and assigns them to an already existing cluster within minutes of their creation. This is very close to being finished. It's quite exciting, actually. And this will be of large help to our analysts. Yeah, so what I can quasi demo for you is this clustering system. So let's say I have an incident ID, it comes in and I'm not quite sure what to do about it. And I want to use this similarity and clustering technology to figure out what to do. So I have some incident ID. This is just some unique marker for the incident, and I can load my cluster model. So this is basically essentially a database of incidents together with cluster labels and some other kind of incident features that help contextualize what's going on. I asked the cluster model to tell me about the cluster to which the incident I'm querying belongs, and it will dump out some summary information about the cluster. So I have this incident, I know it belongs to a cluster of size 7. Those incidents happened on these dates and on these organizations. And the cluster is a little suspicious. Of those 7 incidents, 3 of them have actually been confirmed security incidents. So this should raise an eyebrow. 4 of them are unconfirmed, which just means that no human has made a judgment on them yet. So if we dig a little deeper, this cluster is small enough so we can kind of peek into it and see what's going on with the individual incidents. If there were 10,000 of them, we couldn't do this, but there's only 7. So let's take a look at the individual incidents. So this top row, this is the incident that we started with. And then this column here, the similarity to query incident, this is what the similarity score will tell you is the similarity between each other row in the top row. So you can see that you get this 0.86 score almost the entire time, except for this row where the similarity is a little higher. So maybe this one is worth paying a bit more attention to. And is sort of a quasi explanation of the similarity score. We can list kind of the category of detection for all the detections involved in the incident. And this gives you a hint as to why this is a little bit higher than this. So it contains a type of detection that isn't present in the other incidents in the cluster. Okay, so this is a very, very quick demo about how this might be used in practice. So just to conclude briefly my portion, so these technologies support incident investigation by our analysts and by our customers by allowing them access to information about similar incidents. And that access to information about similar incidents helps contextualize things, helps helps give our analysts some broader knowledge of what's going on. And these technologies allow our analysts to track sort of common activities performed by threat actors. And this helps us kind of maintain a high fidelity detection system. So it's helped weed out some detection rules that were firing way too much false positives. Okay, so that concludes my portion. And now we'll go on to Martin.
Okay, hello. We will save some time and will not switch the screen sharing. So I will be presenting the malware analysis automation platform from here. And we can start by introducing the platform architecture on the next slide, where you can see a lot of systems, which I will try to quickly describe. So the whole automation process starts when a human analyst wants to investigate a suspicious file. For example, when a user reports a suspicious phishing attempt or suspicious email with an attachment. So the analysts get the file and needs to do a quick investigation whether the file is a malware sample or some benign file that looks suspicious. So it starts on the left side in the web UI, which is a simple UI where the analyst submits the file. And this is the start of the automation process. When the file is submitted, the systems persistently store it in S3 data storage. so that we have the samples stored. And once the file is in the storage, the Apache Airflow automation platform monitors the storage, and every time a new file is submitted, it starts the analysis process. At first, it uploads the file into the observable evaluator, which is our developed just support tool that uploads the files into Intel our platform, which queries multiple third-party tools for the analysis. You can see examples of the third-party tools on the right side of the screen. I think everybody here knows VirusTotal, Hybrid Analysis, Alien Vault, and so on. So the automation platforms queries all those tools for their analysis about the suspicious file. When the analysis is done, it's passed back to the observable evaluator. And now why it's called observable? Because it's extract all the observables, which are IP addresses or domain names to which the suspicious file communicates, and recursively analyzes those observables through these third-party tools. So the analysis is run multiple times for each observable, and once each observable is evaluated, the results are passed back into the Apache Airflow. The Apache Airflow takes the analysis of the original suspicious file as well as all the observables and creates a PDF report for the analysts and sends it to the S3 storage back to the web UI for the analysts to look at, and also creates the same report in the form of MISP object and sends it to the MISP sharing platform for other teams to use. The final step is the mitigation of the malicious observables. So if we trust the third-party tools enough that they mark the malicious observables accurately, we can block them through the provided APIs on the infrastructure. So next slide, please. So we integrated all this in a tool that can be deployed using one command in Docker. And the only thing that you have to provide for it to work is API keys for the third-party tools, because they usually require some kind of registration for the tool to run. Their API keys are usually free, but you can buy some better licensing for more throughput or more queries per second and so on. So just provide the API keys in the config file and run the Docker. And now we can take a look at how the system will look like once deployed. So next slide, please. So once the tool is deployed, the Airflow starts the monitoring and wait for any new file submissions. Next slide. Here we can see the web UI for the human analysts to upload the file. And next slide, we can see once the file is uploaded, the Apache Airflow starts the analysis process, and we can monitor the progress of the analysis. And once all of this is green, the report is created and sent back to the analysts. So on the next slide, we can see just the simple UI to download the PDF. And on the next slide, we can see the contents. At first, they are the results of analysis about the file sample itself. So its name, hashes, its other file name variants as seen by the tools, and the results whether the sample is malicious or harmless by the third-party tools. On the next slide, we can see the same for the observables, or in this case, IP addresses with which the malware communicated, and the results whether they are malicious or not. In this case, all of the addresses are Google Play Store used by Google to provide application updates. So they are all harmless, but we can see some tools mark them as malicious. On the next slide, we can see the same in the MISP format, which is automatically shared. And the next slide, basically the same. So you can see the observables in the MISP analysis platform. So that was the malware automation analysis platform. On the next slide, we can see the brief conclusion that it's platform independent, and the main usage is that it speeds up the initial evaluation of a suspicious file. So when the human analysts get a lots of file, he can submit it there and then focus on the interesting or malicious ones. So that concludes my talk, and I will pass the mic to Mischa.
Thank you very much. Hello, everybody. Can you hear me good? Well?
Yes.
Perfect. Okay, so welcome to the last part of the response automation section. I would like to take you to a quick tour on what we have been playing with and developing in Dreamlab. Please take us to the next slide, David. As a quick motivation, we know that Security Operations Center analysts are overwhelmed with lots and lots of alerts all around the globe. And we would just like to automate the repetitive, boring things, so the repetitive, boring alerts, and then free up analyst resources to work on the more interesting edge cases and then do actually some threat hunting. How do we aim to do that? In this work, we use the workflow engine. The first, Zadnik talked about the difference between workflow and Playbooks. This is actually a workflow, so an implementation of a machine-readable implementation of a playbook. We use those and APIs in the SOC or a CM infrastructure to actually sort of simulate actions of a SOC analyst, at least for low-risk cases. This low-risk cases was a distinction that became necessary because we not only wanted to automate things, but we would also wanted to mitigate the risk of doing the wrong thing automatically. So we created a number of different versions of this workflow and thought about what goals we would actually like to achieve with it. And at the end of the day, we realized that we have to distinguish between critical and non-critical assets. So IT assets, clients, servers in your infrastructure. And we basically have two goals with the automation. The first one is that we don't want to act autonomously on critical assets because the risk of disrupting operations is just too high. At the same time, we don't want to miss alerts or just willy-nilly dismiss alerts that involve critical assets willy-nilly, so even if the detection certainty is low. So a simple threshold with the detection certainty will not do. And on the other hand, we would like to automate the treatment of alerts concerning non-critical assets as much as possible. So this is this trade-off that we try to address with the workflow I'm going to show you on the next slides. Please take me to the next slide, David. Yes, so these are the three main protagonists we used in this proof of concept implementation. The first two, the Hive and Cortex, are coincidentally part of Dreamlab's CM solution called CySOC. The Hive is a case management solution. Cortex is an interfacing component between the case management and several external services such as VirusTotal. And then the third party in this team here is Airflow. Airflow is the workflow engine, the same as Martin already showed us in his talk just a few minutes ago. And next slide, please. Yes. So to get a bit of an understanding how this would fit into an organization, we have in a typical SOC very strongly simplified, you have two roles. First, you have a manager of the SOC, and then you have an analyst of the SOC at the very top. The analyst operates or interacts with the CM solution in a SOC, which we've depicted here with the Hive and Cortex. Then you have typically you have one or several detectors on the left side, so the CM solution, which generates alerts. And in our case, these alerts will trigger a run through the workflow that I'm just about to show you. In the middle of all this is Airflow as a workflow engine. This workflow engine integrates with the Hive and Cortex through the APIs I already mentioned. It integrates with an asset inventory, so a configuration management database at the bottom. And this inventory actually contains the necessary information of an asset's criticality. So we sort of invent the notion of an asset's criticality, and we put a number on that. And then finally, Cortex will interact with the asset that is under suspicion that there's something happening there that's not supposed to. Next slide, please. There's a lot going on this slide. We're not going through all the details, but this is the abstracted view of the workflow we've implemented in Airflow and in Python. We already seen a lot about Airflow, so I'm not going to show you the workflow in Airflow again, but this is the decision logic we've created in Airflow. The whole workflow starts at the very left with an alert coming in from the CM or another detection engine. We then start running through and collect some information with the get device info box in the middle from the asset inventory. This includes the asset's criticality that I've mentioned before, and then we have a first distinction where we decide, is this a critical asset? If so, we go up and perform a number of tasks that involve collecting more threat intelligence, and then finally asking analyst what to do. Yes, analyst what to do. If the criticality of an asset is low, we go below, and then we follow an automatic branch in this whole workflow where everything is finished automatically. In the end, with the diamond 2, there is a decision to block or not block a domain, and at the very end, there's a case update where again through the API, the case in the Hive and Cortex is updated with the most up-to-date information. Please double-click to show these two ways through the workflow. So this is this is what we've implemented in Airflow, which brings me to the conclusion on the next slide. As I said, we've tried a number of different ways of creating this workflow. We've seen some things that work. We've also seen some things that don't work. What did we learn? We have about 2 or 3 pages of musings on why or how things work or why they didn't in the respecting SAPPAN deliverable. The 3 most important ones are here. We can say that automating incident response in this way is really possible, but it does require a good risk mitigation strategy that I mentioned in the beginning. So you really don't want to do the wrong thing, and you also don't want to miss out on things that concern your critical IT infrastructure. The second one is that actually implemented workflows, they have to be use case specific. So in this example, it was a DGA detection to make the connection back to what we've heard from Arthur before. And very likely it will also have to be organization specific, because each organization has their specific ways of dealing with certain alerts and with certain detections. And then finally, the devil is in the detail of the workflow design, not really the implementation. So it turned out the implementation of the workflow actually was the easy part, and then turning and twisting things until we were happy with the outcome overall. And here I mean the risk trade-off that I mentioned before. This took some tinkering and actually quite a lot of work, trying different things and different versions of the same workflow. As an outlook, we can say that we're currently adopting these results in our CESN solution. We have this prototype that I just showed you and talked about, and we're currently adopting this into our CM product. And with that, I'm at the end as well of my part. Thank you very much.
Okay, thank you. Thank you for the great presentation. So if you have any question, please try to, you can write it in the chat. Do any question from the audience regarding the response automation and response recommendation? Okay, so I thank the speaker again. Then I go to the next talk. Then the next talk will be presented by Robert and Franziska and Robert from University of Stuttgart, Opportunities for Visualization in Cybersecurity.
Yeah, so can you hear me well?
Yes. Yes.
And you can see the screen in
Yes.
full screen. Okay, perfect. Yeah, so welcome to our talk. My colleague Franziska and me, we are both from University of Stuttgart at the Institute for Visualization and Interactive Systems. And we want to talk about the opportunities for visualization cybersecurity. So visualization has a long history, and it's all about accessing information that is written in data in a visual way. And nowadays, the data has become quite complex, and the data sets we're collecting are very large. So that's why we using visual analytics to come over some of the problems. And first, I want to start with a definition about visual analytics. Visual analytics combines automated analysis techniques with interactive visualizations for an effective understanding, reasoning, and decision-making on the basis of such very large and complex data sets. And frame this, the most important parts are, on the one hand, the automated analysis techniques, and on the other hand, the interactive visualizations, and they work together in somehow an iterative feedback loop, so that we're trying to better our whole visual analytics approach by starting with the data. So we're going to start a mapping and create visualization out of our data, and then use interactions like, for example, zooming and filtering, or showing more details, or transforming the representations. On the one hand, that's like the basic approach how we do visualizations to gain the knowledge out of the data. But on the other hand, we also use automated analysis like machine learning nowadays, where we try to mine out of the data more information, and then also creating data models based on our data. And these models can also be used to can also be visualized and then refined later on. And for example, we could adjust the parameters, or also understanding the model better, and then getting new knowledge out of it to like use it as an input for our new data collection. If we, for example, figure out that we need some new fields in our data tables, that could be quite of value. So that's like the abstract view on visual analytics. What it means for cybersecurity is also that we still have the goal to understand our data, to make sense out of it and to make decisions with it. But also we have the challenges that we have, like dirty data that is incomplete, data that is quite difficult to access. And sometimes also we have the problem that we cannot like really define the question what we're looking to be answered by the data. We sometimes also have ad hoc environments and need for specific situations the correct solution. And especially in cybersecurity, we need this contextual understanding of the data. So we need to know how our data works, how it's got collected, and what information is in the data. And that all makes it difficult to automate processes. So we are still not able to automate like all the different processes, also analysis processes. That's why we are creating visualizations to make that better. So, and we will also start with data in cybersecurity, usually we have somehow network data or endpoint sensor data or data from other external APIs. And what we try to do with visual analytics is bringing all the different data sources together and also find patterns between them. And that's how we that's why we also doing our pre-processing, our data mining. We try to cluster information. We try to make some classification, filters, and aggregate information so that we can align the data, that it works well for us to visualize it, and answer the question we're looking for. And for a human, that means that we need somehow an interface as well, and therefore especially dashboards or visual analytic dashboards can be quite of value because they use multiple views, and there you can like use the pre-processed data and look at it and interact with it. Here I want to show you one example, what we have developed during SAPPAN. We have created the SAPPAN dashboard, and there we can also bring different information together. So for example, we could integrate a guidance by showing playbooks, for example, which a SOC analyst can then be use to look at the different steps which are important. We also have different multiple views on the data. So for example, with endpoint sensor data, where we can look into an host and on the processes running on such an host, but also on the same time can look what happened in the NetFlow data, what happened during the network when we are looking at the host, for example, bringing different multiple views together, or enriching information by like sending some process information to VirusTotal and get an estimation if they are malicious or not. And also we can, in such a framework or in such a dashboard, we can also start collecting the different interactions of such an analyst to use the analysis itself as an possibility to improve processes, to improve collaboration between SOC analysts, reuse it or use it for reporting and accountability. And therefore, we also developed here an provenance capturing tool that captures the interaction an analyst does in our dashboard. And to get more into detail regarding our process tree analysis, one of the visualizations we have as a user the SOC analyst who's confronted with a lot of alerts, as Mischa also mentioned, and therefore we just try to make the data accessible. So we need to pre-process endpoint and sensor data first, reconstruct in hierarchy what was collected by such a sensor, then providing a person an overview, like you can see it here. We have all different activities, and we have with a time bar where you can see when different activities occur. An analyst has the possibility to explore the data, like expanding such processes and the hierarchy on the left side, or hover over such dots which represent different activities of a process to get an idea about what happened on a host machine at this time. And this also leads to analytical provenance data, which we can capture with it. So we can inspect the process information, and we can see like parent-child relationships then. We can see temporal development, and we can also inspect the occurrence of different activities and interact with them. So all in a visual way. And that's about me. I will hand over now to Franziska, and she will talk more about AI for cybersecurity.
Yeah, thank you, Robert. I hope everyone can hear me. At least my window is glowing up. That's always good.
Yes.
Yeah, so now I will briefly talk about AI for cybersecurity and how visualization can figure into that. According to a recent survey by Dasgupta et al., many applications for AI and cybersecurity focus on some kind of detection, like detecting anomalies, malware, a DDoS attack, or an intrusion. So those are the obvious ones. And I think the previous presentations have also shown that this is an interesting area for AI and cybersecurity. But of course, you can also do data analysis and in turn look at data quality using AI. So there is quite a number of ways in which AI can contribute to cybersecurity applications, which makes it quite a good target for increased scrutiny and support with any means available, which includes visualization. And then looking at visualization for AI to kind of bring all the things together. This can be employed to accomplish a variety of objectives, ranging from model debugging during the development phase to communication of findings related to an AI model. In essence, this means that visualization may help to improve or better understand models. It can allow for easier communication, for example, when reporting findings to a supervisor or when training newly hired personnel. And another point, and although this may be more relevant for the future, that's why it's grayed out, it may also help address ethical or legal concerns regarding decisions made by AI or based on its output. And this connects us somewhat to explainable AI and interpretability, which is a topic of interest both to visualization and AI research, and which you may have heard of already. So this has been gaining more and more traction with more and more frameworks and libraries popping up over recent years that let anyone apply newly developed XAI methods to their models and data. There's lots of different methods available, like saliency maps, that show regions in an image that the model focuses on for a specific instance, or in the case of natural language, as you can see at the bottom, you can see which words the model treats as evidence for or against a certain class. So although things like feature visualization in the middle, which can look quite funky and be a little bit hard to interpret. However, as these examples allude to, these libraries are often focused on image or natural language data, which there is a lot of, and require a bit more manual work. So these are more interfaces and libraries and not like complete systems. So you need more work to really allow for thorough analysis for your specific use case. They lack things like connected views and synthesis of different data sources, as well as more sophisticated interaction possibilities. So this means that these methods are quite interesting for visualization that aims to support AI, but may not be easily applicable in any case. For example, when we have data that lacks obvious semantics, like in the case of computer-generated domains. And this brings me to the first of two use cases from SAPPAN that I want to show. This one concerning model analysis for deep learning models. So we've kind of seen a version of this already, though that was an earlier version. So this one combines interpretability with some model debugging capabilities. It's a visual analytics tool that is web-based, making use of D3.js for the visualization and using a Django server with TensorFlow in the backend. In essence, it allows the user to easily analyze training and test data, connect this to model performance, and then also provides an analysis of the model's activations or the activations of the model's nodes for a specific subset of the data, which the user can define interactively using other visualizations. We also provide a decision tree as like a proxy model, sort of a local explainer. And using this explainer together with other techniques like clustering and dimensionality reduction, the user can see how the results from these methods interact to make some sense of the model's behavior, to answer questions like, how does the model go about separating two specific classes? For example, you may have already heard about clever Hans predictors. These predictors come to the right decision, for example, like classifying a picture of a horse as a horse, but base their decision on a wrong feature, like the watermark that is only present for horse pictures. And this illustrates why such questions may be interesting to ask and answer in some way, in order to really minimize making decisions for the wrong reasons, basically, and better understanding where you can improve your model and how your model works in the first place. In this example, so the two images, we see 4 clusters. They are represented by different colors in the scatter plot on the left. Our decision tree, shown as an icicle plot on the right, can separate the 2 classes in this data subset quite well using only the feature top-level domain and length. However, it's not quite capable of separating the light purple cluster in the center from all the noise. So the noise are the black circles. And this may indicate that the model has learned a more advanced feature that's not available in our feature set on which we trained the decision tree. So I think the feature set that we started with was quite simple, mostly containing linguistic and maybe some statistical or other features. And this may be an indicator that these are just not enough to explain what the model has learned to distinguish between the different classes in the data. And then, so going beyond the visualizations that most people are familiar with, such a system requires both domain knowledge and some learning of the abstractions and employed visual mappings. As you may have noticed already, there's quite a bit of explaining you have to do in order to even get some idea of what you're even looking at. This makes it something not really suitable for just anyone, but it can improve analysis by bringing together different views of the data, translating features and relations in the data to visual representations, which are most of the time easier to understand, and connecting them via interaction to provide easy access. Okay, then the second use case in SAPPAN, which you've also already heard about, supports sharing, where federated learning is employed to create a better model for all participating parties, for example, to detect malicious domains. And the idea for this one is quite similar to the other one, but basically transferring it to the federated learning case and making sure of or tailoring it to the peculiarities that this use case has. So this tool aims to let users compare the different models' weight development over the course of training at different levels of detail, because the weights are basically what is shared. For example, the topmost image shows you an overview of weight similarities for all parties per layer. So one spiral is one layer. Each line or each colored line is one party, and the radial lines going from the center to the outer circle are the different training epochs. And we can see that, or rather this indicates how maybe some parties' weights in this particular layer are more similar to another's and how this changes over time. In addition, the user can analyze the model's performance over the training process on a local data set. So here we employ clustering again to find interesting subsets of the data based on the predictions of all participating parties. You can see this in the center right, I think. So there we visualize how these clusters change over time with respect to accuracy, and then also the frequency of the characters in these clusters. So basically, what do the domains in the different clusters look like, and which clusters or subsets of the cluster are similar to each other, in order to get some idea, maybe if things are classified quite differently by different models, why that may be the case, or which parts of the data this affects. So why this particular prototype exposes a lot of data that we would usually not be available to all parties in a federated learning scenario. We would still be interested to test how attacks such as poisoning affect the different visualization components that we developed, and whether this could help in any way to detect such attacks like poisoning or something. Okay, then I think we are finished. With this, we conclude our presentation. Hopefully you found something interesting here. And thank you for your attention. If you have any questions, feel free to ask.
Thank you, Franziska and Robert, for the presentation. There is some comment in the chat. Maybe you can address that.
I'm not quite sure. It seems not quite like a question.
Oh, okay. Yeah, it's regarding the domain-generated names.
Oh, yeah.
Algorithmically generated domain names.
Yeah, I think related to the previous one, right?
Mm-hmm.
Yeah.
Okay.
Yeah. Okay. Okay, so yeah, so then I thank you all the speakers and the participants for joining the event. So yeah, of course, it would be nice to meet everyone in person and having to have the meeting physically. And so maybe for our further dissemination and for our website, for the participant who are interested, please you can turn on your camera. We'd like to take a picture together for the event. So if you feel like whoever wants to turn on the camera, so we can take a picture. Can you turn on stop sharing the screen also? Like okay, Robert, can you stop sharing the screen so I can have a more? Okay, I don't know.
I don't find the button for it. Yeah, there we go.
Okay.
Okay. Yeah.
Okay. I think there are two screens. Maybe can you take the picture?
Yes.
Please, thank you. Okay. So maybe. Okay, so maybe there are also some other participants sharing their screen.
Yeah, thanks.
Okay, so great. And yeah, so again, I thank you all. And if you have any question, you can reach out to me. Like maybe I just regarding SAPPAN project, and I could forward this to the whoever is is doing the actual work. So just let me write down. Okay, so yeah, so then yeah, I think for today we can close the call, and then I wish you all a nice evening and a good working week, and hope you enjoyed our stakeholders event. Bye bye.
Thanks.
Bye.
Bye.
Thank you.
Bye.
Thanks, bye.
Bye, everyone.
Bye bye.
Thanks for attending. Bye.
Bye bye.